I would like to introduce our next speaker, Monty Denneau. Monty joined the computer science department at the Thomas J. Watson Research as a research staff member in 1978. And in thinking about Fred's challenge this morning, where our next John Cocke or similar are, certainly Monty is one of the people that is in the running for that. He has worked closely with John, in particular on the Yorktown simulation machine, and which was based on John Cocke's logic simulation machine. Monty, very much like John, is driven by a passion to build the fastest possible machine. I remember when I first met him in my office, he was describing how he will build the world's fastest machine. He has designed and built several of those, logic simulation as well as the GF11, a machine that's currently running here, and one of the applications that was brought up on it doubled the record for which the Gordon Bell Prize was given for absolute performance. So he at least has done it once. So I would like to have Monty join us and talk about the YSE Eve. Please join me in welcoming Monty.
Where does this go? Oh, like here. Hello. Yeah, works.
Since you wore a tie, we might as well stick it on the tie.
Oh. It didn't go on. Okay. When I heard I had to give this talk, I was kind of enthusiastic because I thought, here's a chance to talk about a truly wonderful invention. And then I woke up a few days ago kind of depressed because I thought the audience is going to be filled with sort of management types, various levels. And I know a lot of them haven't been to the hospital, as Marty was saying, but there's still sort of a loss of brain cells that goes on with, being a manager for any amount of time. However, so I thought about it, but I'm determined that everybody here, absolutely every person, is going to understand at the end of this talk what logic simulation is, how it works, and exactly how John's invention, works. And I figured that's the best thing I can do. So I've stripped everything down to about 8 little concepts, which you'll all understand, and this will do it. Now, I apologize in advance to anyone who knows all this already or thinks I'm oversimplifying. I'm not. This is exactly what you need to know what he did. Now, we're starting really simple here. Remember the audience. A logic value or a signal is something that's 0 or 1. Now, you can think of it on or off, true or false, a light bulb on, a voltage level. It makes no difference. Just think of 0 and 1. Second concept is a gate. You guys who work with transistors, just forget about it. A gate is something that takes in logic values, these 0s and 1s, and it puts out a logic value depending on what came in and what type of gate it is. Now, here's a gate. It's a particularly useful one. It's an AND gate. And if you stick 2 zeros into the AND gate, a 0 comes out, and a whole bunch of other inputs produce 0 output. But if you stick 2 1s in, a 1 comes out. And there's a million other kinds of gates. The top one's an OR gate. You put 2 1s in, a 1 comes out. The XOR gate puts a 1 out if the 2 inputs are opposite. And people who design computers just sit all day at a terminal with these little pictures, and they put them on the screen, they draw them, connect them up together. That's their whole job. Now, this is very important. I mean, I know there are people who don't know this, really. I'm not kidding. A wire takes a logic value from one gate and transfers it to one or more other gates. So you see a little 0 there. It starts at that one and goes along, gets to the other guy. All right, now I have to get a little bit more, just a tiny bit more advanced. It's just a little bit. This is a register. Now, you can build it out of gates, but for simulation, it turns out you want to think about it separate. And all a register does is, instead of just passing things from input to output, it takes a picture. There's a guy standing over here. He's going tick, tick, tick. He's like the clock. Every time he goes tick, the register looks at its input and takes it and puts it on the output and keeps it there. And it stays there until the next tick. You need just one more thing here. Memory, which I'm not going to talk about much here. And memory is a little gadget, has tens or hundreds or thousands of locations, and you can put data into it or take it out from it. All right, so that's our third little concept. Now, we're almost done with the simple concepts. You can take a small number of gates, registers, and memory. You can hook them together, and you can create a useful circuit. Now, here's an example of one. It's the simplest useful circuit I know. It's an adder. I've got an XOR gate, 3 AND gates, and an OR gate. And it takes in three signals, two inputs and a carry in, and it adds them up. It puts out a sum and a carry out. So for example, if the two inputs were 1 and 1, and the carry in was 0, you get a sum of 0 but a carry out of 1. Out of this thing, you can build all sorts of stuff. OK, finally, after just 5 minutes, I'm ready to define a computer. Here it comes. This is how they should define it, because it's very simple. Computer is just a large number of gates, registers, and memory. You hook them together with wire in such a way it does something useful, and you can exchange signals with the outside world. Now, this is it. You don't have to read these big books on like automata theory to understand it. It's the whole deal. OK, now we get to there's only one important question in this talk, and here it is. What are the chances that if you design a computer using about 500,000 gates, it's going to work the way you expect it to? All right, so think about it. Try to answer it. And here's the answer. It's absolutely 0. I mean, no one's ever done it. I certainly haven't done it. I always claim that I did, and then some problem turns up. And it's a real problem. So you have to deal with this in 2 ways. Now, the first way, which believe it or not was practiced up until not too long ago, and well, it's a public talk. I can't talk about particular projects in like Hawthorne, but it's still practiced, is to build a prototype. You just go ahead and build the thing. You say it's not going to work, but we have a bunch of guys. We give them like $3 an hour, and they go and they fix all the bugs. And after like 100 iterations, the thing works. Some of us, and thankfully the company at large, prefers to simulate the design ahead of time and get almost all the bugs out. All right, so that's the end of the introduction. Now we have to get to the serious stuff here. Okay. All right, now this is the intellectual content here. The state of a computer at any time is just the set of logic values on the thing. So if I've got a computer over there and I say, what's the state? You just go around each wire and you measure it. Is it 1 or 0? And you write it down somewhere. And that's the state. And simulation just means you have some guy tick, 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 and look at this little gadget and decide what all the states are going to be. And that's all it involves. Now, as of 10 or 20 years ago, there's a very simple way to simulate circuits called unit delay simulation. It looks a little dense here, but just sort of stretch your mind here. I think everyone can understand this, because it's very important for understanding how John's machine works. You've got this little gadget over there, and it's got states on the thing. You want to update them. So here's what you do. You keep 2 copies of the state, not just 1. They're sort of scratch working copies. You tick the clock, and then you go through the registers and the gates in any order, and you decide what the new output is. And you fetch the inputs to these things from the A state, and you write the results into the B state. All right, so you just picture 2 pieces of paper. You look at the inputs here. You write down new outputs there. Then you take the 2 pieces of paper, you reverse them, okay, and read your inputs from the B one and write the outputs into the A state. And you keep on doing this, and after a while, you'll find out that nothing's happening. The whole thing has settled down. At that point, you can go back to when you can click the clock again. So let me give you a simple example here. This is a 2-bit adder. It takes in 2 inputs, which are between 0 and 3, and it produces an output, C, which is between 0 and 6. So you see A0, A1, C0, 1, and 2 coming out of the thing. And now I'll show you how to simulate this thing using A/B simulation. First of all, we're going to number all the gates. And this is really simple. Just go around. For unit delay simulation, you number them in your favorite order. So I went 1, 2, 3, 4, all the way up to, I think, number 18 there. Every signal has a number. And now what you do, and let's assume we started off, we don't know what the inputs of this thing are, we don't know what the state of the thing is. It's all X's here. And all of a sudden on the inputs, 15, 16, 17, and 18, it's the guys up there on the left, I apply the numbers 2 and 2. This thing's going to go 2 plus 2 equals 4. And so this in binary is 2 and 2. All right, you tick your clock, and now you just do what I said. You go down this piece of paper, you read the inputs, and compute the new outputs. Well, on the first stage, all you know is that the inputs to the register here went through the register and became the outputs. 0, 1, 0, 1 are signals 1, 2, and 3, and 4, which are the register outputs. Then you go back, you do this whole thing again, and now you get some new signals materialize. You see how the X's are filling in here. All of a sudden, signals 8 and 9 up there became zeros. And you keep on going, and by the time you get to here, everybody has a value now, almost everybody. Right here, they have a value. And at this point, you can tick the clock and do the same thing again. And if you went through the grief of looking at what the signals meant, you'd see that the output here is actually 4. So that's your 2 plus 2 is 4. Now, you can't do this on a big machine with pencil and paper, so here's what you do if you're going to write a program for doing it. Well, there's the title, Simulation of a Conventional Machine. And these programs have been written for many years. You have an A state and a B state. Now, in the case of this little circuit, we need 18 locations for A. There are 18 signals and 18 for B. And now you have to store all the configuration information, what type of gate you have and where the inputs are. And so the gate number, whatever it was an XOR. It had 3 inputs. The first input came from location 9, the second from 3, the last one from location 4. And now what your program does is simply go down. It takes each kind of gate. It loads the type of the gate from this section of storage, loads the number of inputs, loads the locations of the inputs, loads the inputs, computes the output, stores the output back. If you're lucky, you can do this in 15 or 20 instructions. And if you code it badly, it can take 30 or 40. Now, the problem with that was that around 1978, if you built a computer with 500,000 gates, you might be lucky to run about 1 clock cycle per minute using this kind of simulation. If you used a method that I'll talk about in a bit, you could get it down to 1 cycle every few seconds. But you want to sort of put like MVS on the machine and simulate some number of seconds of CPU time. It would take years, and it looked very grim. And so John had a very bright idea in the late 70s. First of all, instead of taking like 20 instructions or 30 or 40 instructions to evaluate each gate, why not build a special logic processor that could do 1 gate evaluation per cycle? And here's what it looks like. And this thing actually anticipates a lot of machines that have come out since then. Remember, I had that configuration memory in the picture before that said what each gate type was and where the inputs came from. Well, up on the top, there's what we call the instruction memory. And in the instruction memory, in parallel now, not serially, you have fields that tell you where each input comes for each gate. So the XOR gate we had before gets inputs from 9, 3, and 4, and is going to store an output somewhere. Let's see. OK. Now, the instruction memory is now going to tell data memory where to fetch the values from. The data memory is an entirely separate unit, separate chips. And so 4 units are pulled out in parallel. 4 values are pulled out in parallel now, not like 1, 2, 3, 4. You have 4 redundant copies. They go through a function unit, and the output value is now stored back into a B copy of the data memory, and it's stored redundantly. All the time, a program counter is incrementing and telling you what instruction to do next. This whole thing is pipelined, and so in every tick of the clock cycle of the simulator, you retire 1 gate evaluation. OK, now our 500,000 gate computer can be simulated at 1 clock cycle per second. Well, big deal. You still want to do millions of clock cycles, and it's still going to take a very long time. So John had a second part of this idea that was just extremely bright. He said partition the logic. I'll give you a 500,000 gate circuit. Partition it into, say, 64 pieces and have 64 logic processors. And each one now is going to work on a separate piece of the logic. Now, almost anybody could say that, but now you have a problem. And that's that no matter how you partition it, there's going to be wires crossing these various pieces. And so what about the gates who have inputs that come from other processors? And here comes the best part of the whole machine that makes it really, really brilliant. John interconnected the processors by means of a big switch, called it a cross-point switch. And it's not one of these switches now where you tell the thing what to do on each cycle. You say, I'm going to take the, here's a route, let the data go through it. This switch was compiled out ahead of time. And so in every single gate evaluation, when the processors were evaluating one gate, the switch had been pre-compiled to tell it where to send the data for the guy who needed the stuff. And then these values that went across the switch were stored into extensions of the A and B data memory, so they could be fetched just like normal data. And here's an example. There you see 4 logic processors, and here's the big cross-point switch. And now we're on a particular cycle. We're doing like the 3rd cycle of simulation. The switch configuration memory is saying the first guy should send his results to number 0 should send his results to numbers 1, 2, and 3. And the last guy should send his result to number 1. And so it just goes sort of click, the data transfers, and then on the next cycle, the whole switch reconfigures itself. The software for doing this, which was done by Rosenberg and Cronstadt, Laff, and a bunch of others, involved several things. One was partitioning the logic into processors. If you did it very badly, then you'd spend a lot of time just sending signals back and forth across the switch. And the second one was scheduling the sequence of gate evaluations so that you didn't have switch conflicts. Obviously, the switch can't send 2 guys to the same one at the same time. So you keep permuting your instructions around until the whole thing works out. And it took advantage of something called the rent law, which says that if you got a big enough piece of logic, the number of wires coming out of it isn't all that large. If you had something with 5,000 gates, typically there's only a few hundred wires coming out of it. Most of the signals can be fetched from inside the processor. Now, a 64-way LSM-style machine, actually it's called the LSM, could simulate our 500,000 gate computer, if it had enough memory, at around 60 clock cycles per second, which is really a dramatic improvement. Rick Malm built one of these. I think it was working around 1979. It was used extensively, and people were very happy with this thing. It was revolutionary. OK, that was sort of the first chapter. Now here's the next chapter of this simulation story, which is the development of YSE and Eve, which took place on the order of 1980 to 1985. First of all, I made a bunch of miscellaneous improvements to the thing, which weren't that important. The number of processors in Eve, which is built at Endicott, increased to 256. But the major improvement was to replace unit delay simulation by what's called zero delay or rank order simulation, since it turned out that's the kind of simulation the company did most. And this automatically, with almost no increase in hardware, gave a 20 times speed up. And it works something like this. Remember that adder I showed you before? What you do is you go through and you rank order all the signals in the machine. You start with the registers, you assign them all rank 0. Any output of a register is rank 0. Then you take anybody who's fed only by registers, and he becomes rank 1. Then you take anyone who's fed by registers or rank 1, he becomes rank 2, finally rank 3, and you're done. And then it turns out that if you do the simulation in this particular order, in one pass, you go right through the logic, and you've done your next pass of gate evaluation. You don't have to keep cranking it over and over until the circuit settles down. Now you see we're getting faster here. Eve can simulate our hypothetical 500,000 gate computer now at 6,000 clock cycles per second, which is really getting pretty staggering. And it's hard to imagine the company without that machine. There are a dozen of them in various places. Now, here comes the final chapter, which I can't say too much about because it's still being worked on. But you have a problem if you try to extend this thing to many thousands of processors. And the problem is that you have trouble partitioning the thing and scheduling it. And so one day, after talking to Dan Biese, I had insomnia and had a bright idea, which I can't give much details about, but it's something like this. if you could group processors together, 64 processors say, who could all access the same memory at the same time, and of course you're going to say that's impossible, but so what? And also, if instead of like one switch, you could have hundreds of switches and lots of choices about how to send the data across the switch, then instead of being limited to hundreds or maybe 1,000 processors, you can go up to the order of 100,000 processors, all of them running faster than the original LSM or YSE or Eve board. And so finally, let me summarize the whole thing and what's happened here. The first is that John had just a really wonderful idea. It certainly had a lot of influence on the way I design machines. But secondly, it was also a rich idea. It didn't end back in the late 70s. It just kept going and going. In 78, software simulated our machine at about 1/3 of a cycle per second. The LSM quickly brought that up to 60 cycles a second. YSE and Eve, within just a few years, brought it up to 6,000. And I can't say what here, will bring it up to about 1.5 million cycles per second. And so you have to ask, what sort of things have done quite as well as that? Not many. And that's it.